Hello everyone. Towards this end of the course, this couple of lectures we will see applications of Lyapunov theory, and one of the good applications of Lyapunov theory as as it appears in recent literature is something called Neuro-Adaptive design, which we are going to study in this one or two lectures here. There are various approaches under this title. That means, lot of people will propose different ideas within this framework, but I will take you through just one or two approaches which are very promising. So, this particular lecture will study one approach which is there in the literature for about 10-15 years and it has been applied successfully to a variety of problems in different engineering fields, including aerospace actually. So, that is what I will take you through this particular lecture, and next lecture we will follow up with another approach that we use in our research as well actually. Okay, so we will study this. So, the motivation for this Neuro-Adaptive is perfect system modeling is difficult, we know that. See, first of all you may like sources of imperfections, if you see where this imperfection comes, the first thing is like unmodeled dynamics, means part of the system dynamics you can you may not be able to model, or you intentionally do not want to model, okay, so to have a simplified model. And one example is probably like your number of states are probably same, the state space dimension and other thing remains same, but you intentionally want to like miss some algebraic terms in the model, okay, to have a simplified model, or it is not possible for us to have these algebraic terms actually. Another example is, let us say even if the model all algebraic terms are contained, then the accurate knowledge of system parameters may be an issue actually. Like exactly how do you know what is the system parameter that goes through that. For example, like mechanical system, mass, moment of inertia, all that you can estimate, you can up to a certain level of accuracy. And not only that, the system parameters change during operation as well. For example, like if your aircraft is flying, your continuously your fuel is burning out anyway. So, that particular thing exactly predicting how much fuel is gone and all that is difficult, they will not be able to do that. And let us say passenger movements inside the aircraft. So, even if the mass remains constant, distribution of mass is different, and hence the moment of inertia value keeps on changing actually. Okay, so, these are issues that comes into picture. Then another issue is probably inaccuracy in computations. For example, like if you talk about matrix inversion and all, you may there are some finite truncation may happen, and then this issue comes because of numerical problems and all that. So, the objective here is to increase the robustness of dynamic inversion design, especially in this particular design we have studied in detail from last previous sometime before, I think probably lecture number 30 or around that, and we can I hope everything is clear there, and within this dynamic inversion framework we are going to study how to increase the robustness. Because the dynamic inversion at that point of time we realized that it is sensitive to modeling inaccuracy, and that point of time I also told that we will study an approach to make it robust with respect to this particular issue. So, that is what the primary objective in this particular lecture. So, we want to increase the robustness of dynamic inversion design with respect to parameter inaccuracy and or modeling inaccuracy. So, modeling does not mean only parameter, it can also have algebraic terms missing and all that. So, with respect to that we want to increase the robustness of the DI design. This particular lecture is taken from this. In my view, it was one of the seminal papers actually. The conference version of it probably appeared around 94. The journal version is what you see here is more complete, and the complete detailed analysis and all I think is given in the appendix of this paper. And this particular paper talks about flight control design especially. So, I am not going to take you through details of flight control design per se, but I will take you through details of the method, and then just one or two results that are reported in the paper I will just take you through to demonstrate how this method is powerful actually. But also remember there are variety of versions these authors have proposed, especially Anthony Callis in Georgia Tech and all that, several co-authors with that, and then hundreds of papers have appeared around this theme actually. So, once you understand the basic part of it, probably the understanding all branches out of that should not be that difficult actually. Okay. So, let us talk about what we see here. Alright. So, system dynamics that we are considering here is x double dot is f of x dot and delta. Delta appears to be like a control variable, and intentionally it is taken because delta E, delta A, delta R, all that are flight control variables actually, like control surface reflections and all. And why do we take double dot and all? Because this is one of the forms that appears naturally in system dynamics, and especially if you see Newton's second law, it is something like relates to double dot, mx double dot is f actually, and that is how we start doing that. So, if you really want to control, let us say if you want to design a control based on the attitude dynamics actually. So, for example, that phi theta psi if you remember, then phi dot theta dot psi dot are functions of PQR, but they are not functions of control actually. But if you take double derivatives, then P dot Q dot R dot appears, and then the deltas will start appearing. So, in other words, the flight control problem that we typically interested in is of relative degree 2 actually. So, that is what we are considering here. We in general will take this particular system dynamics, x double dot is f of x dot delta. X is typically not a state variable, you cannot call it that way, but x and x dot taken together will define the state space. Okay. Now, system dynamics that we are considering is in this form, where x and x dot are of n dimensional, they operate in n dimensional space, and delta operates in m dimensional space. So, what are the assumptions? Assumption is first of all x and x dot are available for control computation. Okay. So, they are available with us to use. Second big assumption is m equal to n, that means it is a square system in the sense that x and dimension of x is equal to dimension of delta here. Okay. Remember, x is just half of the state space, it is not the complete state space actually. Okay. So, x and x dot both are like n dimensional thing, but n is equal to m. So, that means x and delta are of same dimension here, which typically happens in flight control design. If you see phi theta psi is R3 and delta A, delta E, delta R are also 3 basically. So, that typically happens that way. Also, there is an assumption that f is invertible for all time, and that is what we need for calculating the control for delta. If you know what is the ideal value of f actually, if you know what is ideal value of f, and that is later on it will be defined as pseudo control actually. But if you know the ideal value of f, what it should be, then this is what it is. So, from extracting delta out of that, what it should be is something like an inverse function. So, you need some f is invertible actually. So, what is the objective or goal here, that x should go to xc and x dot should also go to xc dot actually, where xc is the commanded signal. That is, if you remember dynamic inversion, it is something like star actually, x star. But here I will try to be as compatible to the notations as reported in the paper, so that reading that paper will be also easier for you actually. Okay. So, x goes to xc and x dot goes to xc dot. So, but xc is a commanded signal. Remember, all these are time varying signals actually, they are not constant values and all that. So, how do you do that? Let us say this function is exactly known to us, that means there is no uncertainty and all that. So, that falls in the case of the regular dynamic inversion. And if you really want to have this objective met, then what do you do? We define something like an error is let us say x tilde, which is xc minus x. Either way you can define x minus xc or xc minus x, does not matter really. So, you define x tilde is xc minus x, and we want to design a control delta such that this error dynamics is satisfied. That is what we discussed in dynamic inversion class, right. If it is like E double dot plus k d E dot plus kp E equal to 0 sort of thing, but instead of E we are talking as x tilde. X tilde is the error between xc and x actually. So, if you design delta such that this equation is satisfied, where kd and kp are positive definite matrices, then our objective is met, we know that. Because in that situation both x tilde and x tilde dot will go to 0. If this equation is satisfied exactly, then x tilde and x tilde dot both will go to 0, and hence this both the objectives will be met actually. Alright. So, one way of selecting this kp kd being positive definite matrices is you select kd and kp both diagonal matrices, and you typically select let us say kpi kdi, okay, they are ith element of the diagonal matrix to be positive. And typical way to select it is also like kdi is something like 2 zeta I omega n I, okay, and kpi is omega n I square. So, it will follow typically to the standard form that we know x double dot plus 2 zeta omega n, right, 2 zeta omega n I mean 2 zeta I omega n I x tilde I dot plus omega n square and all that actually. So, essentially we have discussed all that in the I mean dynamic inversion class, and the way to select the zeta I omega n I are to select for this performance objectives like settling time, percentage overshoot, like that actually. Anyway, coming back, so if you select this aerodynamics, and if you know that this system matrix, I mean this function is known exactly, then what do you do? I mean we want to design n delta so that this error equation is satisfied. And if this error equation is satisfied, let us say this is the ith element equation actually, and this ith element equation I can expand it that way. So, because remember x is nothing but x c minus x. So, x I tilde is nothing but x c I minus x I actually. So, the double dot remains there actually. Okay. So, I will retain this as it is, these two terms, but this one I will put it into the definition part of it. So, x I tilde double dot is nothing but x c I double dot minus x I double dot. So, that is how it is. I just expanded this particular term. So, now I want to solve for x I double dot. So, this particular term if I see I solve it for x I double dot, and x I double dot turns out to be all these term, this one plus that one plus that one, okay, right. So, if and this particular term, okay, is something that I define as u I, which is nothing but ith component of what they call, I mean lot of people also call it as pseudo control actually. Okay. Why it is not really the control, but what you really want? You want this x I double dot to behave something like this, okay, where this kd and kp are design gains anyway. So, that is something that we are enforcing, this dynamics is something we are enforcing, this is nothing to do with the system dynamics yet. Okay. So, this particular thing is something that we are enforcing, and whatever we are enforcing is nothing but like a control variable actually. So, that is why it is called pseudo control actually. So, if you see this x I double dot is u I, and it is nothing but ith component of the pseudo control. So, if you repeat this exercise for I equal to I mean 1 to n sort of thing, or you can directly start with this definition and directly get big capital X double dot and all that is also possible, right. If instead of going through the ith component, I will start directly from here and then put it this expression back here, that x c double dot minus x double dot is equal to all that, and exactly like what is going on here. And then I will arrive at something like x double dot is equal to u. This u is nothing but pseudo control vector actually, pseudo control variable in general basically. So, remember. So, what you are doing, I mean in dynamic inversion design, the one way to interpret this design is also like, okay, let me design a pseudo control first, because that is what is meant by pseudo control here. Okay. So, if I design it, then okay, this equation is something that I know, this x double dot is f of this, because that is system dynamics, and this x double dot is something equal to pseudo control that I want to design. So, let me equate the two. It is one and the same thing, whatever way we have interpreted before is one and the same thing, just talking in a little bit roundabout way actually. But a lot of people in literature will talk about pseudo control. So, it is better that we know what we mean actually. Anyway, so x double dot is equal to u, and then x double dot is equal to f of x delta also. So, these two functions let me equate now, and the pseudo control will contain the gains, remember that. So, all these error dot gains and all are all hidden in the pseudo control actually. Now, if this function is exact, okay, then I can compute delta as inverse of that. Remember, this number of equations are same, because number of x by assumption what we started is m equal to n. So, number of states, I mean number of x variables are equal to number of x dot variables, and number is equal to number of delta variables. So, what you see here is the dimension compatibility is there actually, the number of variables are equal to number of equations. So, then we will want to solve delta. Okay, how do you solve delta? Symbolically it is represented as f inverse this. Okay. So, that is where we need the third assumption, and we tell, okay, this function what you have is invertible. If it is invertible, I can talk about inverting this actually. And if it is really like control affine sort of thing, the matter is already there for us to know actually. Like this, suppose it is f of x dot plus g of x x dot times delta, then this delta is directly solvable. I mean that is what we have done before. Alright, symbolically speaking, delta is nothing but f inverse this function. So, as long as we know x and x dot and u contains all that actually, remember. So, that is commanded variable and its I mean commanded variable x c and its the first derivative as well as second derivative. If you know, you can compute all that and then you put it here actually. So, with the information of commanded variables, I mean commanded signal whatever we have and the gains that you are selecting, we will be able to compute this. This is like a regular dynamic inversion actually. Now, where the problem comes? Okay, so, problem comes because of several issues, and one issue is how do I talk about inverse function actually. Okay, in general, I mean if it is a problem function is simple and all that, I can talk about doing an inverse symbolically, but let us say that is not possible in general. So, what the authors have proposed here is, okay, let us use some sort of a neural network to train this inverse function offline. So, I know where my flight dynamics I mean where my flight envelope is. So, within that flight envelope I will train a neural network, and those of you do not know what is neural network, you can think of it like something like a function approximation tool actually. So, this is actually a function delta equal to some function of x x dot u, and you can train this one neural network a priori with the expected values of this x x dot and all that within the domain that you are interested in, and then this inverse function is directly captured using a neural network. This part may or may not be necessary. Suppose you can directly compute delta and your let us say your model of the flight vehicle is in control affine form, then directly you will be able to solve it actually. Okay, so, there is no need of doing this neural network training a priori, but in general it should, I mean it is possible actually. Now, what is the problem? Problem is the model that we started with, this model, there are imperfections because of these issues. Okay, so, that model itself is not good, and then we are also talking about training a network. Okay, any amount of training that you do, this training is never perfect anyway. Any function approximation can never capture a function exactly, there will be some function approximation errors actually. So, these two issues will introduce errors there, and because of which dynamic inversion will not work actually in a very good way. So, how do you improve that actually? That is the problem actually. Okay. So, what we really see here is this, there is an error. Okay. So, can we really cancel that error in an adaptive way? So, we will try to learn that error somehow somewhere and then try to kind of cancel that error. That is the whole philosophy of this neuro-adaptive design, and that function approximation or something that learning part will be done in an adaptive theory based sort of thing actually. Adaptive, in other words, instantaneously you will not be able to cancel, but using the information in a sequential way, then you should be able to adapt your function in such a way that the imperfection will get cancelled out actually. So, let us see that, how do you do that? So, what is the idea here? We want to design another neural network. So, this remember this is neural network 1. So, that is just to have that inverse function ready and all that. So, now let us talk about another neural network 2 let us say, okay, to cancel this error actually. Okay. Now, how do you do that? So, let us say we have synthesized this delta hat actually, okay, using a neural network. So, that is our actual whatever neural network predicts or whatever this function inverse is giving us, that is nothing but delta hat actually. So, what is my system dynamics? System dynamics, if I go back and look at it, this is my system dynamics really, right. Original system dynamics, if I look at it, then this is my system dynamics really. Okay. Now, this delta hat is not perfect by the way. Okay. Whatever is exactly needed for the system dynamics is not perfect. So, what I do, I will kind of let me add and subtract these two terms actually. Okay. This instead of this f of x x dot delta hat I will keep it and I will add this term and subtract that term again. So, that is this is same as x double dot actually. Okay. Now, what is this? Now, let me interpret that this particular thing is nothing but my ideal pseudo control actually. My delta is modified in such a way. Now, delta prime delta hat is something that I am computing with this function, but delta is something else actually. Okay. Now, delta is computed in such a way that is nothing but exactly my pseudo control actually. Okay, that is the whole idea there. Then what is the error? Error is nothing but this minus that. Okay, whatever I have here, this minus that introduces some error actually. Okay, so that error I will call that as delta prime. Okay. Because if I know delta for whatever, if I somehow I know this delta for my exact for my actual system, then that is what I will need for inverting my function actually. Okay. But I do not know that. So, let us see how to synthesize that and all that actually. But essentially this is what if I know that, then I will do this add and subtract operation, and I will see that okay, this is my u plus this delta prime. Now, if I what is my my real x double dot? My real x double dot is my pseudo control, ideal pseudo control whatever I should have, plus the error actually. And hence this entire aerodynamics that we started with, this aerodynamics is not satisfied actually, okay, right. I mean this aerodynamics that we started with is not satisfied, because this is, if it is equal to, I mean that x dot is equal to u, sorry, x double dot is equal to u, then it will satisfy exactly, but it is not u anymore. So, it is u plus delta prime. Okay. So, and then hence if you go back and substitute that, this aerodynamics will not get satisfied actually. So, the error need not go to 0, that is the whole idea there. So, how this operation is going on here, like if you see here, if I somehow know this exact u and all that, let me go through this null network 1, which is the inverse of that function, I will get a delta prime, and that delta prime I will put it through this function actually, okay, and then x double dot will appear, and then I will double integrate, take x and all that actually, and I can do partial integration like 1 by s one time, then x dot will be available, 1 by s one more time, x will be available, I can take signals wherever I want actually. This is just a block diagrammatic representation, nothing more actually. So, mathematically speaking, we are still here, I mean still at the issue that x double dot is not equal to the ideal pseudo control, but it is ideal pseudo control plus some error term actually. Okay. So, how do you deal with that? So, whole idea is, can I design a control properly, so that this delta prime will go to 0 actually, and then we are okay basically. So, that is the observation. If delta prime is 0, okay, then my x double dot is equal to u, and I am fine actually. Okay. So, how do you do that? So, let us talk about this pseudo control fellow is something like ui minus u adaptive hat actually, that is okay. ui stands for the ideal pseudo control, ideal case, okay. Like if the system dynamics is perfect and all that, under those conditions whatever pseudo control is available to us, that is denoted as the ui, that is all actually. Okay. Then this actual pseudo control what I am talking here is nothing but ui minus another term that I am bringing in here, okay. This is nothing but adaptive part of the pseudo control actually. So, this will be computed adaptively. So, ui is nothing but the original case sort of thing, that ideal pseudo control part of it, okay, ideal case, and uad hat is adaptive control to cancel the unwanted effect actually. Okay. And because this entire operation, I mean if you see that the pseudo control modification is going on here, and pseudo control is a concept which is applicable to dynamic inversion only. So, the entire philosophy that we are talking here in this class is applicable to dynamic inversion only actually. It does not probably contain the sufficient generality to apply to any other design actually. So, the method that we will talk in the next class will have that general property basically. Okay. Anyway, coming back to this is what we want. So, u is ui minus uid hat, and ui is ideal pseudo control, uid hat is adaptively what we want to compute basically. So, with that how is the system dynamics behaving? So, if I go back to this error dynamics, okay, that is what I want to see it as 0 actually ultimately. Okay. So, error dynamics is the first term is xc minus the first term is expanded here xc double dot minus x double dot, okay, other terms are kept as it is, and this one I will put it here, okay, this particular thing, and then these last two terms I will keep it together, and that is nothing but my ideal pseudo control. Okay, that is by definition that is my ideal pseudo control. Now, what about rest of the part? Okay, this particular, remember x double dot is nothing but u plus delta prime, that is what we just computed. So, x double dot is something whatever I have u plus delta prime, okay, this is nothing but x double dot. Okay, this x double dot I am substituting as u plus delta prime, and this u is nothing but ui minus uad hat. Okay. So, this u I will substitute as ui minus uad hat. Okay. and this minus will come here actually anyway. So, if I see this is nothing but my u I, this is my u I minus u I d hat, and this is my minus delta prime actually. So, what is getting operated here? So, this entire aerodynamics is not 0, but this is u I d prime u I d hat minus delta prime. So, ideally what should be the objective of this u I d hat design, that is adaptive control design, is to make it equal to delta prime as much as possible. So, if you make it equal, then it is 0, the entire aerodynamics will be perfect actually. That is the whole key idea basically here. So, can we design this adaptive control in such a way that u I d hat will be at least approximately equal to delta prime? We will not be able to do a very perfect job, because any function approximation is also never perfect anyway. So, because of that we will not be able to do, but at least can we make it approximately equal to that. So, the entire aerodynamics will operate like ideal case even with the presence of system dynamics being imperfect, inverses being imperfect and all that actually. Okay. So, that is the objective here. Okay. Now, if this happens, if it is approximately equal to that, then we know that this 2 will be 0 approximately at least, and ith channel will operate something like this, right. If it happens to be like this, then this will be approximately equal to 0 at least. Now, under the anyway, coming back to this, let me again analyze the ith channel of this aerodynamics. Okay, this is the vector sense and all that. Let me consider only ith channel. And ith channel will operate something like that, where this particular term is now a scalar component, remember that. And this is, I did not want to put the small notation and all, because this is what this book follows, the paper follows. Anyway, so this is whenever you see I, subscript I, that means it is the ith component of that vector. So, it is a scalar variable. So, anyway, so this is ith channel aerodynamics happening in, this is also now ith channel. Remember, this is the full vector, but that is now ith channel of that vector actually. Okay. Now, this aerodynamics I want to represent that in terms of state space equation. Okay, let us say now. So, then I will define E as something like x tilde and x tilde dot, standard definition of phase variable form and all that. And then this E I dot, which is a vector equation now, 2 by 1 vector actually. This is in standard vector form. Why do we need that? Because we know the Lyapunov theory is that sort of we want to apply here, is demands that the system dynamics should be in state space form. Okay, so, the double derivative forms and all that are not applicable with respect to Lyapunov theory, that we know actually. So, we want to convert this into state space form actually here. So, this is 2 by 1 state space. For every channel of this error, you will have a 2 by 1 vector in the state space actually. Anyway, so that is what it is. Also remember that because this KDI, KPI is selected to be positive to satisfy that if this is equal to 0, then this is actually like an ideal aerodynamics, right. So, that means the KDI and KPI are selected in such a way that the roots of this characteristic equation are always in the left hand side. And if that happens, then this AI matrix is certainly Hurwitz actually. Okay, because that AI comes from there anyway, it does not come anywhere else, it just comes from there. Okay. The way you write this is state space and all that. So, if you see the eigenvalue locations of this AI matrix is nothing but the poles of this characteristic equation anyway here, and that will obviously this is the aerodynamics that we are selecting, and we will always select a good aerodynamics anyway. That means, the poles are always in the left hand side actually. So, AI is always Hurwitz actually. That is necessary down the line actually. I will again talk about that. And this entire thing what you see in the right hand side is interpreted as something like a control input to this system dynamics here. Okay. So, if I see this xi double dot, and that is what I am writing here, everything here, and this entire term is like my single input control, and what I have is 0 1 here. Okay. So, that is a standard phase state variable form sort of thing, phase variable form. So, ideal purpose, the goal of this UADI hat, the ideal purpose of that is to capture the function delta I hat perfectly, almost perfectly let us say, so that EI goes to 0 asymptotically, but this is difficult to achieve, and hence we aim what is called as practical stability. Okay, what do you mean by practical stability? It means EI will remain bounded where the bound can be made arbitrarily small. So, EI, first of all EI should remain small, but you will not be left with okay this is only bounded and the bound I mean I have to live with whatever bound it pops up actually, that is not practical stability. The bound can be made small as you want, you will not be able to make it 0, okay, but you will by appropriate selection of design variables and all that you can make it small actually. Okay, so, and not only that, the moment this trajectory of the system dynamics goes outside the bound, then it is guaranteed to come inside the bound. Okay. It should not whenever it goes outside it will come inside, I mean that guarantee is always there, and that bound can be made arbitrarily kind of small actually. That is what practical stability means actually. Yeah, that what a lot of engineering problems we are satisfied with that actually anyway. All right. So, if you see this like okay, now coming back to this let us consider okay, delta I prime what we have been talking about. Now, there let us talk about delta I prime hat now, okay, which is nothing but neural network realization of this function. Okay. So, these different notations are necessary because we are talking about different things anyway. So, delta I prime is the ideal error that is there in the system dynamics, and delta I prime hat is a neural network realization of that. So, obviously, there will be an error between the two. There will be like neural networks cannot approximate function I mean with 0 error, and any function approximation cannot approximate a function with 0 error anyway basically. So, because of that there is a necessity to choose different notations and then talk about an error between the two actually. And why is that? Because we will talk about finite number of basis functions. If you talk infinite number of basis functions, probably okay arbitrarily small and error can be 0 and all sort of things, but then we will not be able to do that. And I mean all practical realization, practical implementation will always talk about finite numbers anyway, because each of the basis function will have a weight associated with that, and that weight vector also needs to be integrated in parallel. We will see that as we go along actually. So, we certainly need a finite number of basis vector, and because of that these two are never equal, and hence there is a change of notation actually. And with respect to this particular thing, this neural network, we will talk about this basis functions actually. Okay. This basis function that we are going to use is the notation wise we will define that way, with the corresponding weights of the network being like that. Okay. What is the meaning of that? The meaning is this approximation of this function that I am talking about can be represented as something like that. Something like okay, in the ith channel it is something like okay, if I forget like that, this is like j equal to 1 to some finite number n that we are talking about here. Okay. So, that means is wi prime wi 1 times beta 1 beta I 1 let us say plus wi 2 times beta I 2 is like that, it will continue to a finite series sort of thing. And betas are something that is designed actually, that means basis function are something chosen a priori. Okay. And typically one way to select that is Gaussian network here, because the weights appear linearly. We are talking about linear in the weight network actually. So, if you select this as Gaussian basis function, then the weights people were interpreting that as linear in the weight actually. Okay. So, this is how we will interpret. So, in other words you can write it something what I told just now, I mean this summation sign can be written in a vector matrix way that way actually. So, ultimately what you can write here is UAD I, that particular ith component of the adaptive control can be written as Wi transpose times beta I prime, which beta I prime is the vector, entire vector actually. Okay. So, ideal case when Wi hat is optimized over some compact domain, remember neural networks typically want the compact domain, and compact domains as we discussed in Lyapunov theory some time back, it is something like the set is the domain needs to be closed and bounded both actually, then only neural networks approximations are valid actually. The universal function approximation theory that is there in the neural network is valid only in a compact domain actually. So, that is why it is needed, and most of the engineering problems these are anyway compact actually. So, these will not have those issues actually. Anyway, so when Wi hat is optimized over some compact domain, okay, in this I mean in this set sort of thing, okay, after this optimization over, let the result be Wi hat star actually. Okay. So, that is the very optimal weight after the training is done. Okay. in that sense what will happen, this delta I prime hat star, that is the notation that I will use. Okay. This star is nothing but the ideal function function that is captured, more than that we cannot do. Okay. That is the best thing that we can always do actually. That is something that goes with W I star now, that is the optimal weight actually. Okay. So, that is how I will write it actually, and obviously W I star, W I hat star is something that we do not know, and if we know, I mean directly we will select it and then problem is over, we do not need adaptive capture actually. So, the problem, I mean we know that there exists some weight W I hat star which is ideal, but the value is something that we do not know. So, obviously in an adaptive way we want to go there, we want to approach that W I hat star as much as possible actually. So, in that case this delta I hat prime star is given like that, and this error between these two will remain something very small actually. Okay. So, that is the ideal error of the function approximation, okay, the epsilon I what you are talking actually. So, all right. So, I mean the whole idea is the actual UID hat is given by something like WI hat transpose times beta I prime, and ultimately we will be able to, at the maximum we can go to this WI hat star, and in that sense we will have some function which is delta I prime star hat, and these two fellows will have some errors in between, and which error is that is the ideal function approximation error which are denoting as epsilon I. So, again this algorithm, some sort of a pictorial diagram is something given like this, and I will not discuss too much on that. I mean you get this commanded thing, then you formulate the error, then you pass it through that function, you get this PD part of it, and then you get a adaptive control, then you add and subtract both of that, add XCI double dot also. This one will go through this neural network 2 which is online, this one will go through the I mean this offline thing where this is not shown here, this will go through the, I mean once this is realized, you will take the appropriate signal and then pass it through the offline signal to get the real control actually. So, that part is not shown here. Anyway, that is a function, that is just a pictorial diagram sort of thing, but you can note that epsilon I depends on the following. That means well, this is a spelling error here, it is size of the network. Okay. All right. So, n is I mean epsilon I, the ideal error actually depends on size of the ith network, the choice of the basis function, and accuracy of the neural network. Okay. What is now? No. Okay, let me, this is not required. Okay, and essentially the third depends on first two anyway. So, that first two are primary. So, size of the network and choice of the basis function. Okay. So, that will ultimately dictate how much is a neural network accurate actually that way. So, be careful while selecting the basis function, that is the message actually. Oh, again that is there, okay, forget it. This is same thing repeated, so we will not be able to talk actually. Okay. All right. So, this epsilon I that we are talking here, the error between the two will depend on size of the ith network and choice of the basis functions actually. All right. So, now we will go back and analyze what is going on here. So, what is our estimation error, because this is what is ideal and this is what my actual thing, that is aerodynamics is not equal to 0, but equal to this quantity now sort of thing. So, right, but this prime is not there, I mean this hat is not there actually. Okay, forget this. So, what we are talking here is, let us analyze this particular term now. Okay. Now, if you substitute this quantity, see this one is nothing but the actual weight, this one is nothing but the ideal weight, the basis functions are same anyway. So, I will be able to combine the basis, I mean this W hat minus W hat star here, and write this beta I prime separately actually, this is common to both of it. Okay. So, I will tell, okay, this error that I am looking at here in the left hand side is nothing but the error in the weights of the network times basis function actually. Okay. And also note that this W tilde which is error in the weight is nothing but W hat minus W hat star, and this W hat star is a constant weight actually. So, this does not change with time, because that is the ideal weight, it never changes with time actually, because the function that we are talking here is also like the function that we are talking here is static function. The system is dynamic, that means x double dot, I mean x dot and all that they change with time. but the function that we are talking about in the right hand side of the equation actually, that is a static function. In other words, the function itself does not change with time actually. So, because of that this function is static, and all that is happening here is all static actually. So, that means W hat star is a constant vector actually. So, if this is constant, then if I take time derivative, so W I tilde dot is nothing but the W, right. I mean this if I see this now, okay. Before that this particular thing, if you see here, remember that this W and beta can be vectors actually, even though this is a scalar quantity, this depends on the size of the I mean network and all that actually. Okay. So, that means they are vector quantities actually. Okay. So, if you want, I mean if you want, you can put I everywhere. Okay. This is I here and then I everywhere actually. Okay. So, these are all vector quantities actually anyway. Alright. So, then the to note here is this fellow is 0. So, that is gone. So, that means W I tilde dot is nothing but W I hat dot, that is important to note actually. So, then there is some little bit change of notation and all the authors are using here. So, whenever U appears they call it like that, whenever W tilde appears they call something like that actually. So, it is I mean interchangeably when you mean beta I prime, it can be argument of this or it can be argument of that, and this is used in proof, this is used in implementation. I mean the interchangeably you can use that probably. So, the notation wise, if you have E, then this is the total vector, okay, x tilde dot, and E I means this is what it is actually. So, there are some notations on the way. Now, we will go back to the ith channel aerodynamics, that is what critical thing that we started with. So, aerodynamics, if you go back, okay, this is what the aerodynamics of ith channel. Okay. So, this is where we will go back and try to see what is going on here actually. So, ith channel aerodynamics is something like this. Okay. Remember B is just a 0 1 actually. So, that is given like that. AI is something that we defined before. Now, we will add and subtract this quantity, okay, here, and then I will tell, okay, this is nothing but my system dynamics for the aerodynamics part of it actually. And remember A, as I told that time, is a Hurwitz matrix, because if the characteristic equations are like that with gains being positive actually. So, it is certainly going to be a Hurwitz matrix. Once it happens, and then we tell, okay, now let me try to use this Lyapunov theory and things like that. Now, let us define a Lyapunov function candidate, which is summation over this Vi. Vi stands for ith channel Lyapunov function. Vi is the Lyapunov function for ith aerodynamics. So, I will just consider V1 plus V2 plus V3 up to n, whatever I have actually. Okay. And Vi I will define it something like that, like if it is, I will define some sort of a dead zone. Okay. And if the error quantity norm of that error quantity is defined as pth norm is defined something like that. So, if the pth norm is greater than certain Ei, okay, then I will take it that way. If it is less than that, I will simply consider that part of it. I am now no more worried about minimizing that error quantity basically. Okay. If it is greater than that, I will define Vi to be like that. If it is less than that, I will simply consider that part of it actually. And also remember that by design, okay, this is actually continuous. Vi is actually a continuous function at the boundary actually. Okay. If you consider that what happens equal to this Ei, suppose actually equal to Ei means that is what it is actually, right, isn't it. So, if it is like that, is that. So, when I mean if you see in a limiting sense, when Ei goes to 0 sort of thing, then it will then what will happen when Ei approaches this boundary of this domain, then obviously it will touch that. So, that there is a continuity there actually that way by design. Alright. So, now what is this Pi that we are talking about? This Pi is again a positive definite matrix, which is actually a solution of this Lyapunov equation, and this Lyapunov equation will admit a positive definite matrix because Ai is Hurwitz. That is one thing that we discussed in the Lyapunov theory class, right. I mean use of Lyapunov theory, like if Ai is a stable matrix sort of thing, like Hurwitz matrix, then this Lyapunov equation is guaranteed to admit positive definite solutions for P for any positive definite matrix Q. Okay, that is the theorem that we studied there actually. So, as I told, the by selection Vi is continuous at the boundary of the dead zone. So, that is fine actually. Okay. So, we will consider this Vi as something like this, where Pi is the solution of Lyapunov equation for any positive definite Qi. Okay. So, that is what I told, existence of PDF Pi is guaranteed by the fact that Ai is always, and if Qi is equal to identity, okay, if just I put Qi equal to identity, Ai is something that I know already, right, Ai is something like this. Okay. So, I can actually solve for this Pi symbolically, if I just put identity here and put this thing here, Ai is that. Okay. So, it is essentially a 2 by 2 linear equation. So, 2 by 2 linear equation I will arrange component by component and then I try to solve it for p variables actually, whatever p's are there. No, it is actually p is the freedom will be 3 actually, not 2, because it is a I mean this will be a symmetric matrix where these values are same and these two will be different actually. Okay. So, p will contain, say ideally p is 2 by 2 matrix, that means it has 4 variables, but taking it as a symmetric matrix it will have 3 variables actually. So, 3 equations and all will be available, we will be able to solve it in a closed form way and get it actually. Okay. And you can also verify that if you take any positive numbers for kd kp, then this matrix is certainly guaranteed to be positive definite. You can calculate the eigenvalues and tell okay, when the eigenvalues will remain positive actually. Anyway, coming back to that, that is what we started with the Lyapunov function candidate. Now, let us analyze this rate time rate of change actually, that means Vi dot actually. Okay. So, if you take Vi dot, then you go back to this dynamics in general and then start taking the derivative both sides, I mean right hand side and all that. Okay. So, that will become Ei dot transpose Pi Ei plus all that algebra actually, that goes on with that. Okay. I will not take you through all the derivations because it is anyway there. Okay. Then you substitute for Ei dot here all the terms that you have for Ei dot. Okay. Take transpose of that and put Ei dot, I mean this Ei expression again, sorry Ei dot expression again in the right hand side of it. Okay. This Ei dot is just something that we derived here, this expression. Okay. So, we put it here and then you analyze what is going on, you try to combine terms as much as possible, and this first term here and first term here if I combine, this term pops up and this is nothing but I selected it Pi in such a way that the Lyapunov equation is satisfied. That means, this term is nothing but negative of that quantity basically, right. Lyapunov equation is that. So, instead of that I will be able to substitute minus Qi. So, I will be able to do that actually there. So, whatever terms are remaining is something like this, out of which okay, I will keep something like Ei epsilon I actually. Okay. Epsilon I is something like an error quantity which will come from this quantity actually. If you see this I think we derived it also okay, that right, and epsilon I somewhere, yeah, these two terms will be less than equal to epsilon I. So, that is going on there. Okay. Okay, this epsilon I is coming here and then this Wi tilde transpose appears to the left here and it also appears to the left here sort of thing, because this quantity is a scalar quantity. So, this quantity this taken together is a scalar quantity. So, I will be able to push it to the right if I want. So, I will do that and then take this one common Wi tilde transpose and then this term pops up here, and this is not up to this is equal and certainly from here onwards it is less than equal to, as I have introduced a norm quantity here. Okay. Ideally, if you do not have the norm quantity, they are still equal, but I want to make it less than equal to with by introducing a norm quantity. Now, here is one more problem. Here is something like term that is multiplied with Wi tilde, and Wi tilde consists of both Wi hat and Wi star, and Wi star is something that we do not know actually. Okay. So, unless I know something, I will not be able to tell what is my Wi this quantity, whether it is positive, negative, I will not be able to tell anything actually. So, to avoid the difficulty, what we do is we just put it equal to 0 actually. Okay. So, the coefficient part of it we just make it equal to 0, let us say. So, if the coefficient is equal to 0, it gives you as a byproduct, it gives you some sort of something like a learning I mean neural network learning equation actually. That means, Wi hat dot is nothing but that. So, that is I got one approach of updating my weights, which is nothing but weight update rule sort of thing. So, that is how I derive my weight update rule, but even if I assure that this coefficient is 0, I am still left out with these two terms. So, I have to analyze that actually. Okay. So, this is left out with that, and further analysis will be done that way. Remember, pi is a positive definite matrix. So, there is a definition of square root, and square root can be defined because pi is PDF. And once you do that, then this particular inequality, okay, can be defined something like, okay, this I mean, if you tell this particular quantity is less than equal to this quantity, because any positive definite matrix is bounded between this inequality. We know Rayleigh inequality in matrix theory basically. Okay. So, we invoke that, and then we try to split up these norms and all that. Okay, we write it that way. So, this is also less than, I mean, like equal to this particular term. Okay. So, we invoke that one also, and then tell, okay, if this norm what you see here is greater than equal to that quantity. Okay. So, carry out this little bit algebra out here in the sense of this Rayleigh inequality matrix norm, all that, and then you tell, okay, Vi dot is less than equal to that particular quantity. It feels little bit involved, but it is not once you sit down with the equations actually. You do it one by one term and try to understand one equation at a time, it will not be that difficult. So, I mean, all that is going on here is this is Rayleigh inequality applied here in the negative sense, if you tell that, and it is applied here in the positive sense actually. So, both the times it is applied, and then the square root is split out, and then you do the algebra here. And if you ultimately what it turns out is Vi dot is less than equal to certain quantity like that here actually. Okay. So, that happens, remember this is a positive term here, this is a negative term here. So, Vi dot will become less than equal to 0 whenever this quantity is less than equal to 0. That is the condition that we have to analyze, whether this condition makes meaningful sense or not actually. Universally it will not be negative definite. If it is negative definite, then you are done, but it will not be like that. Under this condition it will be negative less than equal to 0. So, this condition, when you analyze, this condition gives us a very nice condition. It tells us that, okay, norm of Pi is greater than equal to this quantity, then Vi dot is less than equal to 0. Okay. And this norm is actually an error magnitude quantity sort of thing, that has to be greater than the. So, what it tells, as long as this norm or the error amplifies, error grows beyond certain value which is defined like this Vi dot is negative, that means it will try to pull it back inside actually. Okay. But the problem here is this Ei, this entire quantity contains this epsilon I term which is unknown actually. Okay. If I know it, then I have I can compute this thing, but because I do not know it, I will have to do it in some sort of iterative way, and to arrive at a proper value for this. That means I will select one, and then if it is done, then I will select a little less than that, and like that actually. Okay. Alright. Now, coming back, if Qi is equal to I, then this Ei quantity, okay, this is Ei basically, by the way, this definition sense, this quantity is something defined as Ei. Okay. So, if this Ei what you see here, okay, if Qi is equal to I, then this Ei turns out to be like that, because this Qi lambda minimum of Qi is 1 anyway. Qi is identity means all the eigenvalues are 1. So, that is all on 1 actually, denominator 1. So, we will be left out with that actually. Okay. Where Pi is a solution of that equation which is given before actually. Okay. And there is also a very nice theorem in this paper which tells us that Qi equal to identity is not just the simplification of algebra, it also leads to the least bound. Okay. That is what we are interested in actually. It is a simplification algebra, all right, but it also leads to the least bound in the sense of this bound, whatever bound you are showing here, that will be minimum when you select Qi as identity. That is another powerful result actually. Then inside the dead zone, okay, all that happens when when we started with like that, we are analyzing this particular term. Now, within that what you do? I mean, if it happens to be inside, then the weight update rule we are just selecting as 0 actually, that the Wi hat dot equal to 0. That means there is no change of weight after that. So, that is that is what we are doing here. Then Vi dot will be equal to 0, which is, so further error minimization will not happen, or at least it will not grow actually. Vi dot will be assured to be 0 actually. Alright. So, what is the implementation of this summary sort of thing? Okay, you have to select this design parameter, these are the design parameters actually. Wi dot, okay, all that expression we are deriving some sort of a Wi hat dot actually, that means this is a differential equation. This is a differential equation, that is also a differential equation. Okay. So, we all certainly need some sort of a initial condition to integrate this equation, and that initial condition is typically taken as 0, and that actually is also good in the sense that suppose there is no imperfection anywhere, then you really do not need to excite this controller. The adaptive control will not be excited. If the everything is perfectly known and all that, then weight will be 0, it will remain 0 also actually. Okay. The rate of change, this is 0 and that will also turn out to be 0. This equation, if everything is ideal, then E will be 0 and W I dot will turn out to be 0 everywhere. Okay. So, if start with 0 and it will remain at 0 actually. So, that is another good thing. Anyway, coming back, you initialize the W I hat to be 0 for every channel. Remember I is the ith channel of the system dynamics and all. Qi we take is identity, Pi is we evaluate using that formula, that the formula that we discussed actually, this is the formula, okay, you evaluate that, right. Remember this is valued with Qi equal to identity. So, we will be able to evaluate that, okay. And then this Ei is given something like that, which is unknown. So, we will try with iteration actually, we try with epsilon I some value and things like that. But that is primarily for analysis basically. Okay. Anyway, so the weight update rule tells us like this. So, this is this weight update rule will apply as long as this equation satisfied. You can say the Pi norm or something. This norm is defined something like this. Okay, like I define. Okay, this Pi norm is defined like the square root of Ei transpose Pi Ei basically. If that quantity is greater than that quantity, the certain value. Okay, this Ei. And this Ei we have to guess, remember, so selected with that, and then you apply that weight update rule, otherwise it is 0 actually. Okay. So, this is a basis function that you have to select. Okay. This is again this everywhere is prime, so it is also beta I prime. This is we have to select this beta I which is basis function, and gamma should be a learning rate which also needs to be selected actually. Then you compute this adaptive control that way, UID hat, this is the adaptive control part of it. Okay. And then you compute the pseudo control which is like this, we all define on the way of discussion, and the actual control has to be like that, which is inverse of that, which is given like that. So, that is how we compute actually. And the nice results also given in the paper is something like that, the adaptation happens in finite time, it does not take forever to go there, so it does not take infinite time to adapt. And also remember that as t goes to infinity, Ei will lie inside the dead zone, this is something pictorially given, some sort of a dead zone, Ei definition and all that. So, this is like norm of Ei, Pi norm, this is there. So, Ei, if I put a vertical line, this is my dead zone actually, sort of thing. Okay. So, it will ultimately go to the dead zone and it approaches to a constant value actually. So, what is happening? It is, if you pictorially speaking, diagrammatically, if some initially my trajectory is here, it will go here. Okay. Then for some reason, if it comes out, then it will again go, and if for some reason it goes out and again go, it goes out again go and all that. And they have also shown in the paper that every time it comes out and goes back, it will always approach to a smaller value. It will never go back to the normal value and the original value. It will keep, when it goes out, it will enter to that dead zone, but with a smaller value of that actually. So, that is another nice part of it actually. There are several nice things that this paper gives us actually. Now, representative result sense, you see this without adaptive control, this is not behaving very well. So, this is a commanded signal sort of thing, but with adaptive control, okay, this NN1 plus NN2 neural network 2, that is adaptive control part of it, this is very close to the commanded value. You do not see any deviation at all. The moment this plant is something different and all that, it tries to adapt it very quickly rather. Okay. And same thing happens also here. You see then the error between this solid line and this particular thing is so small, whereas if you do not have the adaptive control, this is going very off actually. Okay. And several results are there with a number of papers that I told before actually. It is just a representative thing for you to see, and more details you can always see from the paper actually. These are the references. Primarily I borrowed this from first reference as I told you, but these are also like one more which will tell you how do I use this theory along with the like linear controllers for example. So, this is the paper that will give you. This is another paper for helicopter flight control from the same group sort of thing, almost applying the same theory sort of thing. So, if you see variety of problems they have solved again, and there are various ramifications. For example, they have gone this like reconfigurable control, so pseudo control, hedging and all sort of things are available actually. So, I encourage you to read some of those literature and get comfortable with. With this, I will stop this class. Thank you.